All right, this is the second lesson in chapter 12, chords and arcs. A chord. Now we've looked at a chord before, you just didn't know it. It's a diameter. Okay, a chord, I jumped ahead there. A chord is a segment whose endpoints are on the circle. So any line or line segment that crosses a circle and intersects it in two places is a chord. A diameter is a chord. It intersects a circle through the very center of the circle, but it still intersects the circle in 2 points, so it's also a chord. So in this lesson, we look at a lot of theorems, a lot of different properties of chords, and how they're related to chords and arcs, and their central angles. In Theorem 12.4, and you're going to see a lot of these theorems look the same, because they're referring to basically the same parts, chords, arcs, and central angles. Within a circle or congruent circles, congruent central angles have congruent arcs. That means that these two angles right here, if they are congruent, then their arcs are also congruent, as we studied before. The arcs are the same as the central angle. So if the angles are the same, then the arcs are the same. This little arc symbol is referring to arc AB and arc CD. And then we can reverse that and say that within a circle or congruent circles, congruent arcs have congruent central angles. So that means if the arcs are the same, then your central angles are the same. The next theorem, Theorem 12.5. This one talks about congruent central angles have congruent chords. This is a new one here. So if the central angles are the same, then the chords that are made from the endpoints of the arc are going to have the same length. So if angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. And once again, if we reverse it, we can say that congruent chords have congruent central angles. So if chord AB is congruent to chord CD, then angle AOB is congruent to angle COD. And this is just another way of writing this central angle. Theorem 12.6. Within a circle or congruent circles, congruent chords have congruent arcs. So we made the relationship between the central angles and the arcs. We made the relationship between the central angles and the chords, but now we're going to draw a relationship between the arcs and the chords. So congruent chords have congruent arcs. These are the same length, which means their arc is going to be the same. And therefore, if we have congruent arcs, then we have congruent chords. So let's take a look at our first example. Example 1. In the diagram, VT is congruent to RP. So V to T and R to P. These are two chords that are congruent. So they ask us to write down, what can we conclude? Well, based on those theorems we just looked at, there's several things we can conclude. Because these two are congruent, that means we have congruent central angles. So the first thing we can say is that our central angles are the same. So we can say that angle RDP would be congruent to angle TDV. Second thing we can say is that if we have congruent chords, then we also have congruent arcs. We can say that arc RP is congruent to arc VT. So we can say that these two central angles are congruent. We can say that these arcs right here are congruent. All right, let's move on to another one. Theorem 12.7 says within a circle or in congruent circles, congruent chords equidistant from the center or centers are congruent, which means the same distance away from the center. So if this chord CD and chord AB, okay, are the same distance away from the center, from O to F and O to E are the same, then our chords are the same. So if OE is congruent to OF, then chord AB is congruent to chord CD. And the same thing down here. If we reverse it, we say that chord AB and chord CD are congruent, so therefore the distance that they are from the center would be the same. So understanding that relationship is important to help us solve many of our problems in this lesson. So let's look to see here this example 2. What is the value of x? Justify your answer. Okay? Justifying our answer is just basically going back to our last theorem. So as you look at this problem, we notice that this is 18 and this is 18. That means the total distance of this will be 36. This distance is also 36. So now we have two congruent chords, which means that the distance they are from the center should be the same. So if this is 16, then this x distance should also be 16. And we can justify it by saying, by theorem 12.7. Congruent chords are equidistant from the center of the circle. Next theorem, theorem 12.8. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So if AB is a diameter, and this would be true of a radius as well, if a radius bisects a chord, okay, the same rules will apply here and the same relationship will be discovered. That means that the length of AB is perpendicular to CD, which means it meets at a right angle. So if CE is congruent to ED and CA congruent to AD. So that means that it's going to bisect this chord in half at a right angle. So therefore these two segments are the same and these arcs would then be the same. It bisects the arc as well. In theorem 12.9, if AB is a diameter and CE is congruent to ED, okay? Then AB is perpendicular to CD. So this is kind of the converse of it. Before we said if this was perpendicular to the chord, then it bisected the chord. So now we're saying if the chord has been bisected, then the line has to be perpendicular. Okay, so that tells us we have a right angle. In theorem 12.10, in a circle, the perpendicular bisector of the chord contains the center of the circle. If AB is the perpendicular bisector of chord CD, so if this line here, if we have two lines intersect, one of them is a chord, they're perpendicular to one another, and it bisects it, then this segment right here has to be the diameter because it will contain the center. So let's look at example 3. What is the missing length? In this problem, here's what the information they give us. They tell us we have this segment is 5, this is x, and this is 9. Now, what I want you to recognize is that this has been bisected. This is the center of the circle. So the radius has been bisects a chord, which means that this now is a perpendicular bisector. So that means that we have a right angle. And the radius of the triangle, or of the circle, also provides our hypotenuse for the right triangle. So we have this side is 5, this is x, the length of this is the radius, and this is also the radius, which means that this length is 9. So what are we going to use to find a missing side length given two sides of a right triangle? Pythagorean theorem. So we take the two legs, x squared plus 5 squared equals 9 squared. So we have x squared plus 25 is equal to 81. Next, subtract 25. X squared is equal to 81 minus 25. So 81 minus 25 is 56. Take the square root of both sides, and x is going to be approximately 7.5. Just remember to look for the key parts, the clues. If this is bisected, this is a radius, then it's perpendicular. Or this is not the radius, but this goes from the center. If this continued on to here, it would be the radius. But the same rules apply. If this is bisected, this comes from the center, that means it's perpendicular. All right, you guys try the next one. Pause the video, work it out, and then when you come back on, you can compare the work. Make sure that you round your answer to the nearest tenth. All right, so let's see if you got the right answer. You should have gotten 7.8. So here's where we got our work. X is the hypotenuse of our right triangle, which means it's going to be on the side by itself. 12 is our chord length. Now when they write the 12 in the middle, that means that's referring to the entire length of this chord, which means that if this is perpendicular, that means this chord has been bisected, which means this length is 6 and this is 6. So this is where the 6 comes from as one of the legs of our right triangle. So we have one of our legs is 6, the other leg is 5. So we square both sides. 25 plus 36 gives us 61. Take the square root of both sides to get 7.8. All right. In the next two examples, we're finding measures in a circle. What is the value of each variable to the nearest tenth? I want you to work parts A and B. Pause the video. When you come back, we'll go through and see if you got the right answers. All right, so let's see how you did. In this problem, part A, the full chord is 14. This distance is 3. We have a right angle, so we know it's bisected, which means this is going to be 7 and this is going to be 7. So we have our right triangle. We have 7 squared plus 3 squared is equal to our radius squared. We get 49 plus 9 equals the radius squared. 49 and 9 is going to be 58. Square root, r is equal to approximately 7.6. So let's look at the next one, part B. This problem here we have 11 and 11, which means that it's bisected, so therefore, since this line goes to the center, it's going to form a right angle. Now, this distance here is 15, which is the radius, and because this distance also goes to the end of the circle, this is our radius as well as 15. So we've got our two sides and one unknown. We're going to take 11 squared plus y squared is equal to 15 squared. That gives us 121, 225. Subtract the 121. And we get y squared is equal to 225 minus 121, which is going to be 104. The square root, and y is going to be approximately 10.2. So these are the first two. Hopefully you got these two answers right. So let's try the next two, part C and D. Now in part D, you'll have to draw it on your paper because it was not in the packet. So both of these, we're going to round to the nearest tenth. And so in part D, we're given the information of AB equals 36, CD is equal to 6, EF is 34, and DG is X. find the length of DG. So we're looking to solve for x. So pause the video, work on both C and D, and when you're finished, come back and see how you did. Okay, so in part C, this one can be a little tricky. In this one, you're looking for x, the entire distance of the chord. 5 is the distance from the center to the chord. We know it's perpendicular, which we know that this is bisected. So we're not going to use x as our variable here in our Pythagorean theorem problem. We're going to assign another variable. You can call it whatever you want. I'm just going to call it y. So that gives us two sides and an unknown. The reason why I'm not calling it x, because when we solve for x, if we called it x here, you would just, whatever you get for your answer here would be, you'd put in for your solution, which would be wrong. Because x is the entire distance. Because this is y, it takes two y's to equal 1x. So x is equal to 2y. So as we set up our problem, we're going to have y squared plus 5 squared is equal to 15 squared. So we get y squared plus 25 is equal to 225. We subtract 25. And y squared is equal to 200. So because I'm looking for the full length here, I'm going to put it in my calculator, but I don't want to, I'm going to write down an answer, but I'm going to round it to 4 places. So as I get at my calculator here, well, that didn't work. My Wabbit is moving slow. All right, so we'll just do it here. Apparently that's not going to work. So we're going to take the square root of 200. And that gives us a decimal of 14.1421, 3562. Now, if you're going to write this number down, I would recommend, like we did before, rounding to 4 decimal places. So we're going to write 14.1421. And now we're going to double this because our x is equal to 2y's. So we double this, and that's going to give us the correct answer rounded to the nearest tenth. So if you just wrote 14.1 and doubled it, you'd get 28.2. But as we go back to our calculator, we double this, we multiply this answer times 2, and that gives us 28.28, which would round to be 28.3. So you'd be 1 decimal place off. So that's why it's always good to round to at least 4 decimal places or several more decimal places past the place you're rounding to ensure that rounding, you don't have any rounding errors in your final answer. So our answer is going to be 28.3. So now let's take a look at the next problem. In this problem here, I'm going to go ahead and label everything I know. I know AB is 36. So if this is perpendicular, that means it's bisected, which means this is going to be 18, and this is going to be 18. EF is 34. This has been bisected as well. It's perpendicular, so it's bisected. So this is going to be 17, and this is going to be 17. Now, the distance from C to D is 6. Now, I know many of you are thinking, okay, our answer for D to G would be just 6. But remember that these two chords are not the same. Therefore, they're not the same distance from the center. So what we have to do is we have to figure out the distance from D to G. Now, notice here, we don't have a right triangle set up. We've been using Pythagorean theorem, so let's go ahead and do that. So, what is our radius? Do we have it? This is our radius here. We don't have a radius just yet, so that means we could find our radius by using Pythagorean theorem for this triangle. But if you look at the triangle over here, I'm going to draw the radius here. We only have one side that we know. We're looking for this. This is our x. So this is also our radius here. So we have two unknowns. But in this triangle, we can solve for the radius, which then we could move it and take our answer and bring it over and put it in for r over here. So let's do that. So we're going to take 6 squared plus 18 squared is equal to my radius squared. So 6 squared is 36. 18 squared is 324. Equal to our radius squared. So we add these two together, and that gives us 360 equal to our radius squared. Now at this point we could simplify down and find our radius and then go plug it back in over here. But we're going to do Pythagorean theorem over here again, which means that this is going to be r squared is equal to x squared plus 17 squared. Well, we already know what r squared is. It's 360. So I'm going to bring this over here and plug it in for r squared. So this is 360. We have x squared. And now we're going to square 17. Let's see, 17 squared is 289. So now we're going to solve for x squared. So we're going to subtract 289. So we'll do that in our calculator. We will take 360 minus 289. That gives us 71. 71 is equal to x squared. Take the square root of both sides. And x is going to be equal to 8.426, so we're going to round it to the nearest tenth, which means our x value is going to be a distance of 8.4. All right, this concludes your notes on lesson 12.2. Now you can go and attempt the homework.